Lecture 28 covers section 4.4. At the end of today's lecture, you should be able to apply the conservation of energy as well as the conservation of mass to basic power cycles, in particular, the Rankine cycle. The Rankine cycle is the backbone of land-based power generation systems and reflects one of our most basic heat engine configurations. The Rankine cycle is comprised of 4 open system devices connected in series. If we start at state 1, we have fluid exiting our condenser and entering a pump. The pump receives pump work, W.in, to increase the pressure of our fluid. At state 2, our fluid exits our pump and enters a boiler, where the boiler accepts heat underneath a constant pressure process to increase the temperature of our fluid to saturated vapor. Fluid at state 3 exits our boiler and enters our turbine, where our turbine produces work, W.out. Our turbine rejects a high-quality fluid at a low pressure, at state 4, which enters our condenser. The condenser rejects heat to atmosphere, Q.out, and creates a saturated liquid that then enters our pump. Thus, our mass flow rate through each of these devices is constant. To begin, we'll analyze the ideal Rankine cycle. The ideal Rankine cycle is comprised of 4 processes. As we go from state 1 to state 2, we assume our pump operates isentropically. That is, the entropy at state 1 is identically equal to our entropy at state 2. As our fluid travels through the boiler, we add heat in an isobaric fashion. That is, our pressure at state 2 is equal to our pressure at state 3. As our fluid expands through our turbine, we assume it does so isentropically. That is, our entropy at state 3 is equal to our entropy at state 4. And lastly, as we reject heat from our high-quality fluid that exited our turbine, as we run it through the condenser, we assume this is an isobaric process. That is, the pressure at state 4 is equal to the pressure at state 1. We can visualize the Rankine cycle on a T-s diagram. Consider a Rankine cycle that accepts saturated liquid water into a pump at 100 kPa and inputs saturated vapor at 1000 kPa into a turbine. These 4 individual processes would appear as follows. At state 1, we accept fluid into a pump as a saturated liquid, where we put pump work in to increase our pressure to state 2. As we travel from state 2 to state 3, we are going to do so in a constant pressure fashion, such that state 3 is going to exist as a saturated vapor at a pressure of 1000 kPa. We then expand isentropically through our turbine to state 4, where we have some quality associated with our fluid, and then we reject heat in an isothermal and isobaric fashion till we arrive at state 1. We note the process going from state 1 to state 2 is isentropic, and the process going from state 3 to state 4 is also isentropic. Our processes going from state 2 to 3 and 4 to 1 are isobaric. Considering the conservation of energy equation, if we neglect kinetic and potential energy, our pump work can be described as our mass flow rate times the difference of enthalpies between state 1 and state 2. That is, W.pump is equal to our mass flow rate times the quantity H1 less H2. Now this is a negative quantity, indicating that we have to supply work into our system. Now if we apply the conservation of energy equation to the boiler, neglecting kinetic and potential energy, we see our heat input, Q.boiler, would be equal to our mass flow rate times the difference of enthalpies between state 3 and state 2. Applying the conservation of energy equation to our turbine, neglecting both kinetic and potential energies, we see the work of our turbine is going to be equal to our mass flow rate times the difference of enthalpies between our inlet and exit. That is, W.turbine would be equal to our mass flow rate times the quantity H3 less H4. And last but not least, if we apply the conservation of energy equation to our condenser, once again neglecting kinetic and potential energies, we see our heat rejected is going to be equal to our mass flow rate of our condensing steam times the difference of enthalpies between state 4 and state 1. That is, Q.C is equal to M.H4 less H1.